Good morning. Today is Wednesday, September 24th. Obviously, it's me, Dr. McNeal here. And I just want to say that yesterday's session in both sections of my statistics class was absolute fire. I'm really, really impressed with the students on campus and the students at Donovan as we are really sort of plowing through some pretty dense material. And I just want to give you some additional support and direction about how we reduce data and the two different ways that we reduce the data, definitional and computational formula, and how that connects to probability. I'm going to also show you two additional ways. I'm going to show you how to reduce the data again using your calculator, because that's going to, using the calculator is going to really be an essential skill in the second half of the course. And I'd like you to begin building that skill set right now. I also want to show you how to reduce the data using Excel. So, having said that, let's go to the mat. The mat is what I call working on paper. So I'm going to review the data set that we worked on yesterday. And the purpose is to give you, for anybody who you sort of missed it or rolled over you a little bit, or you didn't quite understand it, I think the extra time and attention may support you, particularly since our midterm exam is coming up in 2 weeks, the first week of October. Actually, October 7th, Tuesday, October 7th. Yeah, Tuesday, October 7th is our midterm. All right, so let's talk about it. We take X, and the data set we used yesterday was 55 4 times. Oops, 55, 65, 60, and 65 4 times. Okay, so that's the X, and we have to decide if this is a population or a sample. We're going to call it a sample, which is why I'm using a lowercase n. And there are 9 in the sample. So to make sure, let's label every X. So you can see where the 9 came from. All right, so the big idea in chapter 3 is or 2 actually, measures of central tendency and measures of spread. So if we look at mean, median, and mode, we can already tell some things about this data, mean, median, and mode. And let's look at the measures of spread. Those are minimum, maximum, range, sum of squares, variance, and standard deviation. All right. So looking at this data, we already know what the median is. It's the one in the middle. The median is 60. There are 1, 2, 3, 4 above, 1, 2, 3, 4 below. That's how come it is 60, right? The mode is 55 and 65. So this data is bimodal. It has 2 modes, bimodal. We don't know what the mean is yet. We haven't calculated it. You remember it from yesterday. I'm going to walk through the calculation. Let's take a look at some of the measures of spread. We know that the minimum is 55. The maximum is 65, which means the range is 10, or 65 minus 55, or 10. We don't yet know the mean, the sum of squares, the variance, nor the standard deviation without calculating them. So let's start calculating them. The first thing we need is the sum of X. Remember, sigma is sum, the sum of X. Put a little I there, meaning all of the X's. When we add them all up, I'm not going to add them all up. You can add them yourself, but it's 540 is the sum of x. Now, if we're going to reduce the data using the definitional formula, we have to figure out what the deviations are of each x from the mean. So absolute deviation, it is x minus m, right? So we need to figure out what the mean is. So since this is a sample, we're going to use m for the mean. The formula for the mean is the sum of x divided by n, or in other words, 540 divided by 9, which is n. That happens to be 60. So now we know what m is, which is 60. I'll just write that here so you can see that we're just subtracting 60 from each of the 9 x's. Right? So 55 minus 60 is -5. We have 4 of those. 60 minus 60 is 0. 65 minus 60 is 5. We have 4 of those. Right? And this is the absolute deviations. AB, absolute deviations. Right? When we add these all up, we cross off these -5s with the +5s, the sum of x minus m is 0. And we know that if it's not 0, we did something wrong. We have to start over to make sure that the deviations are correct. Now we need the squared deviations, because if we leave it this way, it will always be 0. And the formula for that is x minus m, which is here, but we're going to square it. So we're going to square every deviation, including that 0. -5 squared, if you square a negative number, it's going to turn it positive. A negative times a negative is a positive. And when you square a number, it's just multiplying it by itself. So -5 squared is 25. We have 4 of those. 0 squared is 0, and 5 squared is also 25. When we add this all up, this is the sum of squares. So the formula of sum of squares is the sum of all the x minus m, or the squares, the square deviations. 4 25s is 100, 4 25s is 100, so the sum of squares is 200. So we know the sum of squares is 200 from the definitional formula. Let's write that here. Right? We also know that the mean is 60. We just figured that out, right? So if the mean and the median are the same, then the data is symmetrical. If the mean is greater than the median, the data would be positively skewed. If the mean is less than the median, then it's negatively skewed. All right, so we figured out one way to get to the sum of squares through the definitional formula. Let's take a look at it from the computational formula. And it really just is a matter of which is your preference, which is why I'm showing you several ways to do it. All right, so the first thing we have to sort of remember is what the formula is for the computational formula for the sum of squares. The sum of squares formula is the sum of all the squared x's minus the sum of x squared divided by n. Okay, so we know what n is, it's 9, but we don't know what the sum of all the squared x's is. We haven't done that yet. And we don't know what the sum of x squared is, but we know what the sum of x is. So the sum of x squared is like saying 540 squared. Squared. That's the square key right there. Is 291,600. That is the sum of x squared. Now we need to know all the squared x's. So we're going to just square every x value. So 55 squared is 3,025. We have 4 of those. See? 1, 2, 3, 4. Now we have 60 squared, which is fairly easy, but I'll do it also. 60 squared is 3,600. Now we need 65 squared. 65 squared is 4,225. We have 4 of those. All right. So the sum of all the squared x's is the sum of all of this. We can perform that calculation very easily on the calculator because it's pretty uniform. We have 3 or 4 numbers of the same, so 325, 4 of those, 1,3600, and 4 of the 4,225. So using the parentheses key, I can type 3,025 times 4. Close the parentheses, and then keep adding. Plus 3,600. Oops, I take care of this. Plus, open the parentheses again, 4,225 times 4 of those. And now when I press enter, I'm going to, or equal or enter, I get the calculation, which is 32,600. Okay, so now we know the sum of all the squared x's, which is here. We know the sum of x squared, which is here. Now all we have to do is plug in the formula to get the answer. So let's plug it in. Sum of squares formula is 32,600, which is the sum of all the squared x's, minus the sum of x squared, which is 291,600, divided by n, which is 9. So just so that you can see what's happening, we can simplify this division problem, which is 291,600 divided by 9, which is 32,400. So it really is 32,600 minus 32,400. When you perform that, it's pretty easy to see that 32,600 minus 32,400 is 200. So we see that we got the same sum of squares from the computational formula here as we got from the definitional formula here, right? But once you have the sum of squares, you are home free. I'll set this aside. Let's work through the sum of squares, the variance, and the standard deviation. The sum of squares you know to be 200. We saw that in 2 different ways from the definitional formula and the computational formula. If we're computing the variance and it's it's a sample, the symbol for variance as a sample is S2. The formula for it is sum of squares divided by n minus 1. Let's simplify that. That is 200 divided by 9 minus 1, or 200 divided by 8, once you complete 9 minus 1, which is 25, right? 200 divided by 8, 25. Now we need the formula for standard deviation. The symbol for standard deviation for a sample is just S. The formula for that is the square root of the variance, or the square root of sum of squares divided by n minus 1, or the square root of 200 divided by 9 minus 1, or the square root of 200 divided by 8, or the square root of 25, which is 5. So I'm showing you what's really happening. All right, so that's how we reduce the data from its raw form all the way to the standard deviation. So we know that the variance is 25 and the standard deviation is 5. And if you look at this data, you can see that it's varying by 5, which is also the standard deviation. But if we convert this data into a curve, which is really why we're doing this, right? Curve is 0, 1, 2, 3 standard deviations, -1, -2, -3. We know that a normal distributed curve is denser in the middle and less dense on in the tails. We also know that 0 is the mean. We know the mean to be 60. The mean is 60. The standard deviation is 5. That means every standard deviation increases or decreases by 5. So 1 would be 65, 2 would be 70, 3 would be 75. These are the raw scores. -1 would be 55, -2 would be 50, and -3 would be 45, right? 68% of the data, or most of the data, is going to be in the middle. And take a look at where our data actually sits. Our data varies from 55 to 65. That's the minimum and that's the maximum. We can see that that corresponds to how it looks in the shape. We know also that the formula for converting a raw score to a z-score is the x value minus the mean divided by the standard deviation. We can test this out to confirm that 60 is actually 0. All right, so if we say we want to see what 60 is. 60 is the score that we're checking. 60 also is the mean divided by 5. 60 minus 60 is 0. 0 divided by 5 is 0. Right there. If we wanted to see 65 again, 65 minus 60, which is the mean, divided by 5. 65 minus 60 is -5. -5 divided by 5 is 1. Or sorry, 65 minus 60 is just 5. Sorry, mistake. 5 divided by 5 is 1, which is right here. All right. So that should give you a review of how to reduce the data using the definitional formula, the computational formula. I want to very quickly show you 2 more methods. One is the calculator and the other is Excel. All right, so we're going to use the same data. Let me get the calculator ready. I'm going to reset it by pressing second, and reset. It's asking, do you want to reset? So move over to Y for yes. That's a little bit better. So the memory is cleared. Now I want to prepare the calculator for data, second and data. It's asking me, am I using two variables, an X, one variable, an X, or two variables, an X and a Y. I'm only using an X, so just say enter there, and then just press data. So now it's ready for X1. X1 is 55. 55, press down. I'm going to keep going. Let's just press down. So now it's ready for X2, 55. X3, also 55. X4. X5 happens to be 60. X6 is 65. 65, 65, 65. All right, so that's 9. All right. So now that I've entered all the data, I could go back all the way up to X1. Oops, I keep going past it. Yeah, I can confirm that X1 is 55. It's the X2, 3, and 4. X5 was 60. X6 was 65. 65, 60, right, that's just to check. Now I'm ready to calculate it. So I press star variable. It tells me that the n size is 9. X bar is the mean. It's telling me that the mean is 60. You can see that. Now it's going to tell me what the standard deviation is if it is a sample. The sample standard deviation, which we've already figured out, was 5. If the data were a population, the standard deviation would be different. It would be 4.71 for population. We can go on, it'll tell us what the sum of X is, which is 540. It will also tell us the sum of all the squared x's, which is 32,600. So the calculator really does all of the same things that we just did on paper, and it did it much faster. So I want you to be familiar with the computation, the definitional formula, the computational formula, and how to do it on the calculator. I'll show you one more thing. Let's clear the calculator. Second and reset, and move over to yes, and then second and data. We want one variable again, and data. What I want to show you now is how to enter data very fast when you know that you have multiples. I have 55 4 times, 60 1 time, and 65 4 times. So I don't have to key it all in. Watch this. So 55 for X1, then asks me what's the frequency. We have 4 of them, so type 4, press down. So now it's ready for X2, which is now 60. Now it's ready for X3, and it's 65, but there are also 4 of those for the frequency. So I made far fewer keystrokes and got the same thing. So I'm gonna press star variable. Look, still, the n is still 9. And the x bar, or mean, is still 60. The standard deviation for the sample is still 5. For a population, it would be 4.71. The sum of x is still 540. And the sum of all the squared x's is still 32,600. This would probably be a good time to, if we entered this information into the calculator and we needed to figure out the variance and the variance and the sum of squares to go backwards. Remember that? So if we have the standard deviation of 5, right? The variance, since you go from the variance to the standard deviation by the square root, we would just square it. Now it's 25. And how we go from the sum of squares to the variance is divided by n minus 1. We're going to multiply it by n minus 1. 25 times 8. 200. So there you see how we went from the raw data to the standard deviation of a sample, from the definitional formula, from the computational formula, and with the calculator. And if you're using the calculator and you have to go backwards, if you have the standard deviation, you can work backwards up to the sum of squares. All right, so now I want to show you one more way to calculate the data, and that's using Excel. Excel is a program that not a lot of people have comfort with, but you should, because when we get to correlations, I'm going to perhaps invite you to use Excel, because it just might be easier. I'm going to put the data in column B, so I'll very quickly add 55, 55, 4 55s, a 60, and then 4 65s. Is that 4 or 5? There we go. Oops, a little bit wide, bigger. There, you can see it easier. All right. So this is the X column. Okay. So the first thing we need, of course, is the sum of X. The formula for that is equal sum, left parentheses, and then grab and drag down. You can see those are what we call ant trails around the data, and hit the, oops, there we go. Try it again. Equal sum, there we go, right parentheses. 540 is the sum. Let's calculate the average. Excel has a function for average. Again, it's equal. Every time you want an Excel function, you use the equal sign, average. And the left parentheses again, grab the data, so you see the ant trails around them, right parentheses, and we can see that the average is 60, all right? Let's do our absolute deviations, which is taking 55 minus 60. And because I'm doing that again and again and again, I'm just going to drag the formula down. And so it's just sort of copying the formula, but making it contextual to that row. So if you look here, the very first column I said is B2, which is right here, minus 60. But when I copy this down, it says B3, which is here. This one says B4. This one says B5. And so it copies it all the way down. I'm going to also use, I'm going to copy this over. So this looks at column B, from B2 to B10. This one looks at column C, from C2 to C10, because all it's doing is summing the same range. Now we need our absolute deviations, or sorry, square deviations. Let me move this out of the way. I'm trying to get a superscript, yeah. that, I need a superscript. Format cells, superscript. Okay. Okay, so now we just need to square every x equal this. And the feature for squaring is caret, which is shift 6, 2. Okay, I'm going to copy that down. I'm going to copy this over. So now that is the sum of squares. Okay. Now let's do the same sum of squares, but let's use the computational formula. So this is really the squaring every x. So I'm going to go equals every value here. I want to square it. All right, I'll put a comma there. All right, and I'm going to copy this down. All right. I'm going to copy this formula over, and again put a comma there. So 32,600. So the sum of squares, if we're using the definitional formula, let's say sum of squares, definitional formula. Sum of squares, computational formula is the sum of all the squared x's, which is here, minus the sum of x squared. We don't have that yet. Yeah, sum of x squared. Really, it's just 540 squared. 291,600. Okay, so now we have all the pieces. So the computational formula is the sum of all the squared x's minus, I'm going to use parentheses, the sum of x squared divided by n, which happens to be 9. 200. Same thing. All right, let's move. But once you get to the sum of squares, you know you are home free. So sum of squares. Right here. Variance, standard deviation. The sum of squares we know to be 200. The variance is 200 divided by 9 minus 1, or 8, which is 25. And the standard deviation is the square root equals square root. That's the formula for square root. Oops. Square root of 25, which is 5. Now watch this. We can actually get all of that done in one step in Excel. We can ask Excel to give us the standard deviation. Remember that the standard deviation for the population is a different number than the standard deviation for a sample. So Excel has a feature or a function for standard deviation as STD. And when we're talking about a sample, it's STVD.S. Again, we're going to just grab this data. And it's 5. Standard deviation sample standard deviation, population. Let's see what that same data would be, but standard deviation for a population, 4.17, and it keeps going. We only need it to go out 2 decimal points, 4.71. And if I jump back over to the calculator, you will see that the standard deviation for a sample is 5, and for a population is 4.71, blah, 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 but we round it down to 4.71. All right, so hopefully this is a good refresher and prepares you for Thursday's class, which will be pretty active. I'm offering 25 extra credit points for anyone who brings in by hand, handwritten, this reduction of this data set using the definitional formula and the computational formula, all the way down with the measures of central tendency and the measures of spread. If you bring 2 copies and put them on my desk tomorrow, I will give you 25 extra credit points. My goal, my intention is that through practice and exposure, you're going to learn this in a way that is very different than just listening to it or watching me do it, but you have to actually do it. You have to see yourself write it all out. And through writing it out, you're going to actually learn it. So having said that, nice work yesterday. I'm looking forward to our work tomorrow. And again, our job is to prepare for the midterm exam that's coming up in 2 weeks on October 7th. All right, have a good day. See you tomorrow.